So welcome to the last edition of the Seminário de Álgebra this summer. Yes, I know we haven't had many editions, but let's just hope that things get better. But today we have a double edition. That is, we're going to have two speakers. And it's my pleasure to introduce the first speaker, Daniel Barrera, from the Universidad de Santiago in Chile. And he's going to talk to us on arithmetic manifolds and elliptic curves. Okay, please.
Obrigado pela invitação. Muito contente de falar aqui, mas eu gosto de falar português, mas eu vou falar em inglês, senão misturo tudo. Então, vou tentar falar em inglês. Então, é 50 minutos, não? Tá bom. Então, vamos lá. Perfeito. Então, so I want to speak about arithmetic manifolds and elliptic curves. And so I will explain a little bit about the context firstly, then to speak about the name of the object here. So then some application of these ideas. So one application I will try to give an idea how you use these objects in number theory. So this talk is more algebraic number theory. Okay, it's not totally algebra in this seminar, but it's algebraic number theory, so it's a mix of stuff. Okay, so I would like to explain you where a panoramic view, where below these kind of ideas of these objects that we are using. So let's explain a little bit about the context of this object. So because we work in algebraic number theory, also we consider numbers. So we look at these kind of numbers. Or we are more interested about these other numbers that maybe you know, these algebraic numbers, which are numbers such that are the roots of polynomials. No? So there exists a polynomial with coefficient in the rational number such that vanish in alpha. So these are called algebraic numbers. Okay, and in algebraic number theory, so we are interested in study that kind of this field. We are interested in to try to understand this field. Okay, so to try to understand directly is a little bit involved. So you try to understand some symmetries of this field. So instead of precisely that, instead of Q bar, we try to understand the symmetries of Q bar, which is called as the Galois group. No? So it's called. Oh, let me write on the other blackboard. So this is the group of symmetries. This is the Galois group. So this group is a very big group. It's a hard topological group. So it's not very easy to describe it. It's difficult. So now, you want to try to Q bar. So you try to understand the symmetry. So this is still difficult. So you try to understand the representation of this group. Okay. So we try to say something to consider, no? To understand representation of this group, and it's naturally a topological group. So you try to understand the continuous representation of it. No? Representation of this Galois group. Okay, so this kind of representation are appear naturally in algebraic geometry. So let me give you one example that will be turning around the talk during all these 50 minutes. So the example I want to give is about elliptic curves. So fix an elliptic curve. So let E be an elliptic curve. So the size of the letter is fine, so you can read it. It's okay. So long that I didn't give a talk on in public, so it's very difficult to. Okay. So would you fix an elliptic curve over Q? So my goal is to give an example now. No? You fix an elliptic curves over Q. So what some of you know is it's an equation. No? It's y squared. Some equation like that, where A and B are rational numbers. Like this, they are satisfy some conditions such that you have no multiple roots here. So in some way that the curve that you can draw is smooth. So the condition is the discriminant of that is 4A. Okay. So that is an elliptic curve. So from this geometric object, you produce some example of representation in the following way. So what you do, you take this. So first you take the solution of this elliptic curve with coefficients in Q bar, the field that we are interested at the beginning. Then, so you have naturally here, this is a structure of abelian group. There's an algebraic way to describe an a structure of abelian group, and so you can speak about the torsion. Okay, so the points such that some power is the unity. So you take the torsion for some n. Then you take the inverse limit of it. Everything is compatible, and you produce this object here. Okay. This object has a name. It's the state model of the elliptic curve, and normally you note like that. Okay. That is it's a definition. So you can prove that this Z is a. I need to introduce some notation. I will come back over this, but this is. I will recall what is that in a few minutes, but that is periodic numbers, periodic integers. Okay, but I will come back in a few minutes about that. And you have naturally here an action of the group you are interested in. Okay? So this object gives you an example of a continuous representation of this group. Okay? Okay, so that is an example. You're interested in this, but so there is some conjecture that describe this kind of objects. So that is called the Langlands program. So let me. That's some ideas that come from Robert Langlands. So that was in the 60s, and he said that. What you want to understand, you can describe in terms of analysis. So, but okay. So, he proposed the following picture. So, from one side you have some natural. So you will consider some continuous representations, but you will consider some of them which are natural. Some natural continuous representation of this group that we are interested in. So some natural means, I will not be precise, but conjecturally means that you can describe in terms of algebraic geometry. So So you put a lot several conditions here that at least you expect that they come from algebraic geometry. That is one side, the side that you are interested to study. And he proposed that they are the same, that here is obscure, but I will come back on it in a few minutes. So automorphic representation. Okay, so there are these two worlds, and what Langlands proposed is that there is bridge between both. Okay, in this direction and this direction. So there should be, there should exist some bridges between both. So this program is a famous program that people start from this year until now. A lot of people is working on it. And so before to explain some details, to enter some technicalities, let me say something about these bridges. So firstly, in this side, you can find this example that we have here, the Tate model of the elliptic curve. And here to say something, here appears something that called modular forms. Maybe you're more familiar with it. Modular forms. Okay? So this object here disappearing in analysis. Analysis. And more analytic objects. They are in fact the representation of some reductive groups. Okay? So representations of reductive groups. Okay, so on this side, it seems a little bit technical, everything, but you have a lot of techniques. So there exist a lot of techniques. A lot of stuff that you can do, a lot of technique methods. In particular, you have something in particular. For example, on this side, you have the arithmetic manifolds that are in the title. Okay. Okay, so that is the new side that I didn't say nothing precise, but I will come back in a few minutes, as I said. And in this side is the side that you care about, so our motivation starts from here. So here there are important problems. So important always is relative, but important problems. And in fact, these important problems are very precise conjectures and very famous conjectures that in some way they are guiding the method that you have on the right. So they help guiding the automorphic method. Sometimes you need to know what you want. You have method to use, but this say, oh, you can go in that direction, and that help you to prove something. One example of important problems are the block-Kato conjectures. I think that there is two kinds of block-Kato conjectures. One more K-theory that I know nothing, but these block-Kato conjectures are related with L values. And this is a generalization of Birch-Swinnerton-Dyer conjectures. So this is the flavor of these block-Kato conjectures that relate L values with the arithmetic optical representation. Okay, so that is more or less the context in which we are placed. Okay, so my goal now is to explain a little bit what you can find in this side, and then how you can use these tools in some way to prove something on this side. Okay, so I will. That is my my goal. Okay. There is a question about this first part. So in any case, if there is any question, you can just stop me. Okay. So finally, I will come back to arithmetic manifolds. So now I will introduce what that means. Okay. To define these arithmetic manifolds in general, as I want to give you some idea of it, so we need some rings. Okay. So let me introduce some rings just because we need them, but it's interesting. So let's start with this result. This is a famous result at the beginning of the 20th century that say that when you have a non-trivial absolute value, a norm of the rational numbers, not just the rational numbers, okay? So you start with the rational numbers, and you look all the norms on this field, okay? That is absolute value. Norm is that they respect the product, only have triangle inequality, okay? You can classify them, okay? It's a theorem of Ostrowski that say a non-trivial absolute value of Q is equivalent to one of these two absolute values. So one natural absolute value you have in the rational numbers is the usual one, no? The usual one. I mean, if there is a positive number, you keep just the number. If it is negative, you put a minus. That is the usual one, okay? And you have this absolute value. Is it typical to remove it or to keep? It's better to keep this mask, no? No, maybe I will keep. No, no, I will keep. Okay, so it's equivalent to the usual one, or one more different one is called the Eladic one. Eladic absolute value. So where L is some prime number. Okay, so there are exactly these. All the absolute values are or the usual one or some Eladic for some L. So there are infinitely many absolute values, but very precise. Okay. So what is the consequence of it? Okay. So when you look at the rational number and you want to do a completion, you need to complete with respect to a norm. So that tells you that you have two kinds of completion of the rational number. So there are only two types of completion of Q. One is the real numbers, and the second one is the completion with respect to this more fancy absolute value, which you call the QL. And the name of, you call this the Eladic numbers. Okay? And these two kind of completions are very different, okay? But similar in some way. They are parallel, but you have different behaviors. So there are some differences between these two fields. For example, when you look at the unit balls of this, when you look at the unit ball of these two kind of fields, I mean when the norm is smaller or equal than 1, In the first case, you obtain the interval, minus 1, 1. In the second case, you obtain a ball, which normally you denote by CL, ZL, which was the notation that I use here. Okay, so these are called the Eladic Integers. Okay, and one big difference between these two situations is that this one is a ring. Okay. Okay, so that changed a lot the situation. This is a ring here. Okay? So this is one difference that you have. So now I will introduce the rings that I need to define these arithmetic manifolds. Some definition. So we define the following topological rings. Okay, so the idea is that you want to put all this information together, but there is some issue with the topology. So you would like to take just the product of them, but you need to do some modification. But at the end, morally, you are taking just the product of them. Okay, so you consider A will be the following tuples will be some infinity components and some finites at primes. This is an element of the product that you want. Okay, but these issues about the topology you restrict a little bit, and you ask that AL is in this unit ball for almost every L. Okay. You call also AF. That is when you put all the information together. You put AF will be the same, but without the information at infinity. Okay, so the condition is the same. And finally, you define the Eladic integers, the integers version of this. So you take just the product of all these rings. So these are 3 rings that we are introduced. And then they have names. So these are the adels of Q. These are the finites adels of Q. These are the Eladic integers. Okay, so we just put all the information together in the way that is, you have a good topology. I didn't precise the topology, but okay. So now we will define finally what is arithmetic manifold. So, and first, let me give you some remarks relating this subject. So naturally, you see that this one is inside these ones. Yeah. Okay. Now you can put the rational numbers that you are interested. So we start with the rational number. You remember? So we take different completion of it. So you can put this inside of this diagonally. So one interesting fact is that when you put the rational numbers over each component, is dense by construction. But when you look at it inside of this huge ring, this is closed. This is okay. So it's a big difference. Okay, and in fact, I think it's discrete inside of that. Okay. Okay. So that is some rings. So now let me introduce finally what is an arithmetic manifold, and to give you an idea of of the situation. So you fix k with that this. Oh, I forgot to introduce something before. So fix g. So if you remember when I made this kind of picture between these two worlds, on the right-hand side is an analytic world. There was automorphic representation. That was representation of something, of some group, okay? And this theory is parameterized in some way for reductive groups, okay? So we will fix one, and we will use this to perform some construction. So fix G, an algebraic reductive group over Q. Okay? So I will give two examples in a few minutes, but you can think about GLN, GL2 over Q, GL3 over Q, JSP, JSP4, etc. That is an algebraic group. Okay, so the arithmetic manifolds are attached to some group G, and you have plenty of them for each group. So fix, let's K will be some, this will be a subgroup of this group. These are the points of G in this ring that we already introduced. And you have a natural topology here induced by the topology of the AF. And you take the K will be a subgroup, will be open and compact. Okay? So here is this. You need to think about the level. This case is the level of your arithmetic manifold. So the arithmetic manifold of level K. So here I should say that is arithmetic manifold for G, but I will avoid to speak about G. So arithmetic manifold of level K is the following double equation. So it's given by the following a little bit. So we will denote it in this talk by xk. Okay. By definition, will be the following. So you take the adelic points of your group, I mean this huge group, and you look the Q points inside of it through this diagonally, okay? And on the right, you quotient by K, which is your level, but just have information at the finite places. You need something in infinity, and you add something at infinity. At infinity, you add the following. Okay, so that is the arithmetic manifold. And I need to precise what mean this information that you put at infinity where. So ZG just is the center of G normal, not only. And K infinity is a subgroup of the real points of your group G. And this is a Lie group, so it's just fix one maximal compact. Okay. Yeah, a maximal compact subgroup. Okay, so that is finally the object that we are interested in, which are the give rise to the title of this part of the talk. Okay, this is an object that appears on the automorphic side, automorphic representation, and these are very useful in arithmetic, let's say. So let me just give explain a little bit what you can do with them, maybe, or some division that you have between those. So you have two classes. So you have two types of these arithmetic manifolds, okay? And that's depend of G, okay, not K. If your group G satisfies some conditions, so the arithmetic manifolds are good enough, good for something or not for something. And the point of view is with respect to algebraic geometry, okay? So you have two classes. Let me do that here. So one is when xk is, so no. Let me firstly observe that these are not algebraic varieties at all, okay? So remark. So if you look at this quotient here, this is morally a quotient of the Ali group by an arithmetic group, subgroup, okay? So a priori it's just a real manifold. It's a real manifold. And in this generality, you cannot say anything more, okay? But you have two cases that you are interested. You can split them here now. Okay, so one possibility is that this real manifold is in fact an algebraic variety, okay? One case is xk is admit canonical structure of algebraic variety, okay? And in fact, not just over the complex number, but over the, let me write in this way, a canonical structure of algebraic variety. Let me write in this way, structure of a canonical complex structure. It's more complex structure. And when you have this complex structure, in fact, you have a structure of algebraic variety or some number field, okay? And in fact, a model, a structure of algebraic variety over a number field. Okay, so that seems a little bit strong. So, but there is a huge theory that study this case. They are called the Shimura varieties. Okay? Okay. And in fact, you have a complex structure, but in fact a model over a number field, for example, Q, a finite extension of Q, and there you have a strong connection with arithmetic. Okay, so that is one case of this object, and we're writing this. And the second case is not. So you have not that. Okay, that is the two cases that you have. Okay, one example that you have here, in the case, in some way, this more algebraic situation, is, for example, one example, it can be, take G, GL2 over Q. Okay? GL2 over Q, and, okay, for example, take K equal K0n, or any number, and this will be the matrices A, B, C, D, GL2 AF, GL2 Z bar, such that n is a device C. Okay? So it's a special case of this general situation that we have here. We're taking K, this open compact subgroup, a very specific choice of it. Okay? So what you get is here, xk, the arithmetic manifold defined there, is, you can look really quickly, that is isomorphic. You can describe in terms of more classical terms, something like that, where H is the upper half plane, and gamma 0 n is this, this famous group, is A, B, C, D, but now they are in S2 Z, the matrix with coefficient in the integer number, such that the determinant is 1. Oh, such that n divides C. Okay? And there is this very famous curves that are called modular curves. And as you know, these curves, or maybe some of you know, these curves are, so if you look at this, it's a real dimension 2. But in fact, it's a curve as an algebraic curve over the complex number, and you have a model over the rational numbers. Okay. An example in the second side is, for example, if you take G, GL4 over Q. Oops. Okay? GL4 over Q. You take any open compact K, and if you look at this arithmetic manifold, you will see that these have the real dimension 9. So there is no possibility that you have a complex structure, and even less possibility to descend to the rational numbers, so real numbers, or finite extension of Q. Okay? But the interesting thing that I would like to say that in both situations you have application to arithmetic. Okay? Here is more direct, as you can see, because already you have algebraic variety or a finite extension of Q. So you feel the relation to arithmetic. Here is less obvious, but still you have connections. Okay? And around these topics, there is a lot of research nowadays. And one last comment is here, in fact, is repeating what I said. Maybe you have the tools that you have here is naturally algebraic geometry with all this you can do there. And some tool is, for example, in this situation, some tool is that the singular cohomology. Algebraic topology or singular cohomology. And this is also very powerful to do a lot of things. Okay? Okay, so that is more or less what are the arithmetic manifolds. And now I would like to explain some kind of application belonging more or less to the first class of curves. Okay? So as I told you, there are applications on the second kind of curves also, but okay. But I will concentrate on the first one. But this is very active nowadays. I want to say that you cannot forget that. Okay, so let's say some words about. I don't know if there is some question, maybe. About the time, I have still 20 minutes or something like that.
Maybe some more 10 minutes, I guess.
10? Oh. We start a little bit late.
Because real dimension 9, could it be a real break variety?
Yeah, I don't know.
Yeah. Sometimes your number field is a real number field.
Yeah. Yeah, I don't know. So. It's a question that also I try to understand, but okay, so let's explain a little bit. Okay, so the kind of things that you can do, I will give some ideas now, is about elliptic curves, which are an object that you have a lot of problems there, a lot of conjectures. But I hope that I will have time to make the connection between what you can do here with elliptic curves and with arithmetic manifold. If not, it will be a disconnected talk maybe, but let's try. So, conjectures on number fields. So the idea of this work, in common with 3 colleagues, is to relate conjectures. The first kind of conjecture is about number fields. So let's fix a number field. F be a totally real number field of odd degree. What means that is odd degree means that the degree over Q is odd, and totally real means that it's real and very real. So for every embedding of F in the complex number, the image is inside the reals. Okay, so we will start with this F will be our fields. And let's explain one conjecture that there is. It's a very old conjecture. It's very easy to state. So we consider the integers of F. Okay. Inside, you can consider a subgroup. Yeah. So we will be the unit of this ring, such that they are totally positive. So for each one of these embeddings, they are real numbers, so you ask for that. Okay. So consider this group. This is a group. So in fact, it's a group. So in fact, it's a Z model then of rank. You can calculate his rank. It's very precise, and that is a very old theorem. The rank is the degree of the field minus 1. Okay? So the conjecture of Leopold is the same is true periodically. So let's state the conjecture. Conjecture. So this is Leopold. Leopold is in like I think it's 60s. Okay? What say this conjecture? So you fix a prime number P, okay, and you look at this E, but inside of something for more periodic flavor. So you look at the OF tensor ZP, okay, and you take the unit here. This is a subgroup here. Here you have a natural periodic topology coming from the periodic number, and you can take the closure, the periodic closure. And the conjecture of Leopold say that this is the same rank as before. So it's a ZP model of rank. This is the conjecture. It's very easy to state, but seems very difficult to prove. Okay. So that's a conjecture on the side of the number field. On the side of elliptic curves, let's on conjectures for elliptic curves. Okay, so we need to start fixing an elliptic curve. So fix A via elliptic curve or F, FB, elliptic curve over F such that is modular. So this condition allows to relate all this stuff with arithmetic manifolds. But I hope that I will have some time to give some words about that. Okay, So you fix this elliptic curve, and you fix a character of the Galois group here involved. So now it's not the Galois group over Q, but it's the Galois group of over F. Okay? So you take a character of finite order. Okay? So one important invariant attached to this data is the following: is LEKS is be the it's an L function, twisted L function of E. Okay, so this I will not give the definition, but it's an L function like the Riemann zeta function, like the Hasbel zeta function of an elliptic curve. But here you twist a little bit and you modify it. So let's just say that it's holomorphic in all the complex plane is entire in, I think it's holomorphic in all the complex plane. Okay, it's an entire function. Oh, sorry. On the complex plane, and when you look, so that makes sense to look at this value. You look at the evaluation at 1. So this is a complex number, but this number has a lot of information. So at least conjecturally, oops, this number has conjecturally a lot of information about the elliptic curve, in particular about the arithmetic of the elliptic curve. Okay, so let's state the conjecture. This is the Bloch-Kato conjecture in this situation, and then I will explain what we prove. Okay, so conjecture. That is the Bloch-Kato conjecture that I said before. This is like in the 90s was. And that relates this L value to this value is non-zero, the non-vanishing of this value, you relate with some arithmetic information of your elliptic curve. So if you look at the solution in Q bar of your elliptic curve, this is a Z model because this is a abelian group. Oops. You can tensor with Q bar, and then you have an action of the Galois group. And then you can take the part killed by, where the action is given by chi, okay? And this is 0. Okay? So that is the Bloch-Kato conjecture relating the arithmetic of the elliptic curve twisted by this character and the value of something, the L function. So as in the BSD conjecture, Bayesian conjecture, relates some analytical information, which is you take all the local information of the elliptic curve together and you package it and you obtain some global information. Okay, so there is a p-adic version of it. So fix p prime, fix p a prime, and you can have a version of this Bloch-Kato conjecture but p-adic. So p-adic Bloch-Kato conjecture. Okay, so the first part of this conjecture is, okay, you have a p-adic version of this number. So there exists a canonical analog. All these words, canonical, I need to precise, but I will not. So a canonical analog of this number, we will denote by, we just add a p here, a subscript p to say that it's the p-adic version of it. And this is a number and will be in here. Okay? And the second part of this p-adic version of the conjecture is that you can relate again this number with the arithmetic of the elliptic curve. So this number is non-zero, then the same here. Okay, So this kind of periodic analogs of conjectures in this block cut or virtual diagram is always, this is complex and this is global. This is periodic and this is still is global. So you just modify what you say in the this analytic part. So, okay, that's are the conjectures. Our result is mix them, relate them. And I will stop with that maybe, but if I have time, I will give some idea of the tools. Oh, yeah, oh. Okay, but what, okay. Let's just state the result. And so the final part is the theorem. Oh, the theorem with two colleagues. Is that we relate these two conjectures, okay? So there exist infinitely many primes P such that the following. If you look up Leopold, the Leopold conjectures for F and P imply periodic block cut for the elliptic curve and this character. So that is what we prove. Okay, so that is the theorem, which is still in, we are writing it. So let's say here it's in progress. Okay, so we are writing the proof of the theorem, and that is what we prove. To prove the theorem, we use the arithmetic manifold. So I had one last part about flavors of the proof, which is 5 minutes, but maybe I over already, so I'm not sure if that's, maybe I will, I don't know.
Can you make it shorter? 5 minutes?
4? Yeah. Sorry. Okay, but so let me maybe just a few words to connect both. Okay. Okay, so we have arithmetic manifolds, and now we state some very algebraic maybe results. So let's introduce which are the, I will just say which are the manifolds that involved in this proof. Okay, so this is the fourth part. Okay, which are the objects that we are using? So that's come from the modularity. Okay, modularity. Oh, let me first something I will state before. So first you explode the modularity linking to arithmetic manifold. Secondly, you use the ideas of Euler systems. This is I wanted to explain something here, a few words about that. That are very powerful tools that come from, that was introduced by Francisco Taine. That he was at IMPA. He made a master and a thesis here in IMPA. And when he introduced these ideas, reading works of Kummer, it was very new ideas that he works at the level of number field, not elliptic curves. But then quickly were developed by Rubin, Kato, and there was at some time that there was not a lot of works about that, but recently, by the last 10 years, there was an explosion about these ideas by Darmon Roger, and mainly they start the new explosion of these ideas. Darmon Roger 10 years ago, more or less, with Bertolini, and nowadays it's a lot of works on that, but it's someone from the IMPA that started with that. So I wanted to say that. So what's mean that is the study and production of classes. The classes that you produce and you study are here, are some Galois cohomology with coefficient in the Galois representation you have here. Okay, so that is the idea that introduced Tynes. So it's a formalism to study these classes. How to produce these classes here. We know how to study them, but how to produce them, so it's linked with these two, with modularity. Here appear a relation to arithmetic manifolds. XK, I will call it. I will not say which is the group, but the group, the reductive group behind is attached to a quaternion algebra over F. Okay? And then appear naturally some arithmetic manifold linked with the elliptic curve. There is a lot of work on that, and for us it's an assumption. Okay? But how you explode that, you use the cohomology of XK to produce these classes and periodic geometry. Okay, so mixing this, so you use étale cohomology, coherent cohomology, and rigid cohomology, different kind of cohomology of the curve. You mix with periodic geometry and you produce some classes there, you study them, and you linked with L values. Okay, so that at least give an idea how you relate this tool of arithmetic manifold with this kind of problems.
You said you have been able to prove that for infinitely many primes, but for how much of them, like the density, is it very big?
Oh, firstly, you need to ask whether the P is totally split
Okay.
in F, so that you already have 1 over the degree of F over Q. And then you need one more information to study some eigenvariety. Then maybe there needs to be less than that.
Okay. But do you have an idea about the density? Is it
less than 1 over the degree of F over Q?
okay? Okay.
But depend on other work that we are using about some geometry of some periodic variety. But it's depending of.
Any more questions? So I just have a surprise. Cauchy?
I also, it's not Cauchy with Y, it's Cauchy with I.
Okay.
Very,
very close still. But
it's an Italian version of Cauchy.
okay.
I also was surprised when we started working because I was thinking, wow.
Okay. Wow. All right. So if there are no more questions, then we're going to make a break of 10 minutes. Just 10 minutes, huh? Enough for coffee, and come back, and we come for the second session. Okay, thank you again.
Thanks for the invitation.